Hey, this is Bottom, and we're going to be talking about Game Theory, Discussion Part 3. So, in the discussion so far, we've talked about the general approach you should have when you sit down to play a game, and how you can use population tendencies to accelerate that game plan you have. So the game plan, right? You start off with an equilibrium strategy, and then you move to a maximum exploitative strategy ASAP. So we're going to do an example of, you sit down, you play a game, what happens, and how you should approach it. And again, this is opinion. This is my opinion. This is not something that's, that I can prove with math that this is going to be the best thing to do. But in my experience, this is the best thing to do. So let's say you're playing even and odds, or odds and evens. This game was explained in the video where we talked about computing Nash equilibria using the indifference principle. So I'm not going to restate the rules. Go check that video if you forget. So let's say you're playing the role of Evan. So you're evens in this game. And you played 10 games against Oliver. And so let's say he throws 3 ones and 7 twos. In the first 10 throws. Alright, so what should you do? Well, first let's let's do the robotic thing, and let's show how to systematically figure out what to do. So let's say that we're going to set Q to be the probability that Oliver throws 1. So our guess, the data says Q is 3/10. And now we say, what is the EV of we throw 1 versus the EV of we throw 2? So when we throw 1, remember it's the probability times the payoff plus of the first outcome plus the probability times the payoff of the second outcome. So let's say the first outcome is Oliver throws 1. So this happens with probability Q, and the payoff is 1, right? Because 1 plus 1 is even. And then probability 1 minus Q, he throws 2, and that's, we lose the game then. So if we throw 2, then with probability Q, he throws 1 and we lose. And with probability 1 minus Q, we win. So, we can simplify these a little bit. This is just Q, and this is 1 minus Q. So remember, we had that Q was 3/10, so so the EV of throwing 1 is 3/10, and the EV of throwing 2 is 7/10. And we want to maximize our EV, so of course we should do the thing that maximizes our EV, and that's this. So we should throw 2. And again, my advice do this until Oliver changes. So what do I mean when I say changes? Well, keep a running tally of how much he's throwing each, and maybe when he's thrown more ones than twos, then switch to throwing one or something like this. But until he really sort of makes you think twice about throwing two, you should just keep throwing two. But this is, I'm sure you could have figured out, you could have come to this conclusion on your own without having to do this calculation. And so why is that? Well, the reason is because you know the Nash equilibrium already. So let's talk about that. So the fastest way is to use the knowledge of the Nash equilibrium. So the Nash equilibrium is 50-50, right? We know that at equilibrium, these numbers should be 5/10 and 5/10. So compare 3/10 to 1/2, and you conclude that he doesn't throw one enough. So when I say when he doesn't throw one enough, what do I mean? I mean he doesn't throw one enough to make us regret throwing two. Oops, sorry. So we can just compare to the Nash equilibrium and quickly come to this conclusion. So we haven't calculated our EVs by doing this, but we do get the same answer. We do figure out what to do without having to do a calculation. And so here's something that took me a while to really get my head around, which is that you don't really need to know the EV of something to know that you should do it. I mean, if the right thing to do is the right thing to do, it doesn't matter how much you're winning or losing by. It's still the best you can do. So this kind of quick way to just compare the frequency that your opponent is making a certain move to the Nash equilibrium will tell you what to do, and it won't tell you how good it is, but it'll tell you that's still the best thing to do. And of course, why wouldn't you do the best thing to do? It doesn't scratch that itch, that curiosity itch that you have, that you want to know how well you're doing. But here's how you would do it if you really do want to scratch that itch, and you'll quickly see that eventually it becomes tedious and you just want to know what to do, and that's the most important thing. So this is an example of how you can use, so how you would approach a game in a concrete example, and also this is maybe the second thing that we've come across that really makes us want to know the Nash equilibrium, which is not only does it let us. So the first reason was that it lets us be defensive. And the second reason is this example here is that it quickly lets us figure out how to mount an offense against our opponent. We just look at their strategy, we compare it to the Nash equilibrium, and we immediately know what our maximal exploitative strategy is. So it's good to know the Nash equilibrium.